The other time we're talking about fluxes, and then we go here, we talked about momentum flux, we talked about energy flux, mass flux, and molar flux, right? So then, let me see if I can go over. So momentum flux, right? Flux is quantity per unit area per unit time, right? So momentum, right? We talk about momentum, we're talking about mass here. So like mass, right? Let me use this one. So this is the momentum side, and then we'll have the area side and we'll have the time side, right? For energy flux, right? So energy, right? Per unit area per unit time, right? For the mass flux, there's this side. We have the mass here. We have the unit area and we have unit time, right? For the molar flux, we have mole, we have unit area, we have unit time, right? So today we'll try and then continue from here at the fluid statics and this application. What they say is that now we are studying the nature of fluids before we do any analysis. So you see, remember, initially I drew this thing. This is, you'll be seeing this almost all the time. So like, I'm trying to get you familiar with this particular diagram and then the concept behind it. Are we okay? So then here, then we are talking about the nature of fluid. We are saying that a fluid is a substance that does not permanently resist distortion, right? So like, meaning that we know for solid, generally they can resist distortion for a long time. But what this particular statement is saying is, if I have a fluid, like something like this, within fluid on its own, like a whole fluid, and then whole fluid, and I'm considering just a portion of that particular fluid, it's saying that if I try to maybe apply some kind of shear stress here, to get to a time where there will be shear, it doesn't permanently resist the distortion. Like, so I'm applying a particular force here, like a hand or something is here, or maybe a particular surface is here, and I try to move that particular surface. Let me redraw this one. So let's say I have a, what's the name, a fluid, right? Let's say this is a cylinder. Then again, if cylinder, meaning that we are using what, cylindrical coordinate system, right? And then let's say the fluid is inside this portion, right? And then this is just one plate, a stationary plate. Let's say it's between two plates. So if it's between two plates, no longer a cylindrical coordinate system, right? You talk about that one, but I'm just giving you the gist of how it all goes, right? So if this is a stationary plate, it doesn't move, and this is a plate that can move, I can accelerate it, or I can maybe let it move at a particular velocity, meaning that it will have a particular force, right? So if I try to, this is a fluid, and I try to move this plate here, it will kind of cause some distortion within the material, right? If that particular material is not able to resist the distortion permanently, we say that particular material is a fluid, right? Okay, so we are seeing during the change in shape, shear stresses exist. Okay, so you see, I'm having a fluid within two plates. This is a stationary plate, this particular one is a stationary plate, this is a moving plate. So you see that I'm applying a force to it, right? So the plate is moving. So if the moment the shape of the material begin to change, so if you remember from physics, shear stress, like I'm having a material like this, and I try to apply a force in this direction, even if the material to be like this, it will experience some shear stress, and then it will be end up being something like this, right? There will be some distortion in the material, right? So whenever we apply, whenever a material is not able to permanently resist distortion, we say that material is a fluid, right? And they are saying during the change in shape, shear stresses exist. Okay, a fluid in equilibrium is free from any shear stress. Okay, so then you see generally this where shear stress has occurred because I've applied the force and then the material has sheared, right? This is the original position of the material we are considering, but then it has changed to this direction. Are we okay? This particular direction here, I mean, the material has experienced distortion. So we are seeing whenever a material is in equilibrium, it is free from any shear stress. Are we okay? There is no shear stress applied to it to cause the material to distort anything. Are we okay? Yeah. So then, incompressible fluids. When I try to compress something, what happens? Let's see. Let's do this. Oh, sorry. Let's say I have a balloon, right? Balloon. Right. It's not fully filled to some point, right? If I try to maybe use my hand to point here to maybe push it in that direction, right? Do you see, if the immediately you move your hand, it comes back to the original position, right? Yes, just an idea. But we are saying that an incompressible fluid is a one whose density does not, only changes slightly when moderate changes in when there are moderate changes in temperature and pressure. So like when I try to, there's the balloon, maybe I point, I think you've experienced that before, like I push my hand in the balloon a bit without trying to burst it or something. You see that it just shows some depression, but the moment you move your hand, it comes back to its original shape, right? So that particular case, in that particular system, okay, you see, whenever we are doing momentum transport, anything we are talking about, we are saying we are in a system. Are we okay? So in this particular case, we are saying the balloon is our system, right? The filled balloon tied with a tire or something is our system, right? So it's experiencing some small depression, and the moment I release this force here, or I remove my hand, it comes back to its original shape. So in that particular system, I can see the fluid in the balloon is incompressible, okay? And then when something is incompressible, what do you think happens? Let's say I have a fluid. This is air, right? So let's say I have a liquid in a particular between two plates, right? And I try to apply force here, right, by any means, and then it's not going down, right? It's not showing any changes, right? We can see that the density of the fluid doesn't change. The reason why we can say that is that every material is having a fixed density, right? And the moment you try to, maybe you compress it on something. Imagine you have a bread, right? Butter bread, like the one we generally know, and then I end up compressing it to this size. The same bread, though, you see that this one, the density of this one will be lower. Like, so density here will be lower, but the density of this one will be higher, right? Yes. But for this case, if that particular material managed to withstand the force that I'm applying on it and it doesn't change the shape on anything, it's incompressible, meaning that the density doesn't change. And if something does not change with respect to time, right, I can write this, sorry, what is not changing? Density, right? So the density, or the rho dt, is equal to 0. So this is another way of expressing or saying that a fluid is incompressible, writing it in math, like, or using equations. You get that point? Instead of saying a lot of things or saying incompressible fluid or something, I can use this equation here to describe the fluid. You get the point? Yeah. So a compressible fluid is the one that experiences significant change in density, right, when you apply a stress or something. Are we okay? Yeah. So liquids. So you see, most of the times when you have liquid, they are incompressible. Gases. So you see, this one, though it experiences some form of depression and then come back to itself, I'm able to compress it, right? So air or gases are compressible, right? Fluid. But if I have two fluid here, like fluid between two plates, and I try to compress it in this particular case, it won't compress or anything. It won't change its dimension. Are we okay? It doesn't compress. So liquid are incompressible. And then we are seeing that pressure exists at every point within a volume of fluid. Are we okay? These are, again, you see when we started, we were seeing basic concepts, okay? Basic concepts are the concept that you have in mind, right? When you get this concept in mind, and then maybe you are doing something like, let's say, heat and mass transfer, or any scenario you are trying to analyze, or any momentum system you are trying to analyze, it helps you to understand them very well. Are we okay? So then we are saying we have a volume of fluid, right? Something like this. Or even, yes, a volume of fluid, let's say in a container like this, right? We are saying at every point within that volume, pressure exists. So like if I'm able to see, which is not possible with my naked eye, and let's say a particle here within that particular, let's say there's a liquid within this container, and I look at this particle here, and like I'm trying to zoom in, that's why I'm doing this, right? I've zoomed in. So if I zoom in, I have the particle here. It's saying that at every point within a fluid, pressure exists. So like from one direction, this direction, like every point within the fluid, pressure exists. Okay. Pressure is a scalar quantity, meaning that scalar quantity, what do they mean? Right? So at times what you've learned already helps you to go ahead of what you are doing later. So scalar quantity means that it has only magnitude, right? It doesn't have a specified direction. So you see, coming from this direction, this direction, this direction, this direction, not from a particular direction. Okay. So at any given point, the magnitude of pressure is the same in all directions. Okay. The reason why this comes here is that we are seeing that we are assuming that the liquid in that particular container is in equilibrium. Equilibrium means that, like, it's kind of static, right? So you see, we are doing fluid statics. So we are assuming that that particular system, this particular fluid here, is static in that particular container. the total force on that particular liquid in the container is 0. So meaning that it's not moving, it's just where it is. You get the point, right? Yeah. So at every point, the magnitude of the forces at every point are the same. So like static, okay. So yeah, this is an interesting diagram, but just to give you the idea, and we raise another point here. So remember, in I'm sure you've seen this before. Like you have something like this, a container filled with liquid, right? And then probably you've tried the experiment before, or maybe you've seen it somewhere, right? So, and you have a container and then filled with liquid, and then 3 notches or 3 indents have been made in that container, right? The moment this is done, you see that the liquid that comes from here will travel a higher distance, right? And followed by this one and then this one. Let me use different colors so that it's much more clear. So if I use red here, this one will travel a longer distance, right? Followed by this side, right? And then finally the top side, this side, right? So you see that what it's saying is that you've seen this diagram before. So like, yeah, I'm sure, but if not, you check it out. Okay, yeah, pressure at different points within a fluid. Okay, so it's the same thing here, but just that this is more real. How do I see it? Applying it to a bigger system. So they are saying that within a pool or something, or within a particular system, so this is like the exposed surface of the liquid within this particular system, right? So this is the container. It could not even be a container. It could be just maybe a river or something with uneven bed. Uneven what's the name? Yeah, seabed or like riverbed or something. Get the point? Yeah. So what it's saying is that when you have what it's saying is that, let me magnify so we see what's happening. Okay, so they've identified some points within the system, right? So we have point A, B, C, D, E, F, G, H, and I, right? You see the written some equation here, pressure, P at A, P at B, right? Yeah, and this is PATM, this one. So this PATM here is what is showing here, right? So it's like atmospheric pressure that is kind of like exerted at the surface of the liquid within that particular container. Are you okay? And the rho GH here is potential energy. Okay, yeah. Okay. What it's saying here is that you see the written PA is equal to PB, PC, PD, up to G, right? What it's saying here is that within a particular system, at a particular point within the system in equilibrium or a static fluid, are we okay? Let me use a ruler to make that line clear. Forgive me if this line is not straight, but I think I have to draw it. So from a line here, straight line. I'm using freehand, that's why it's a bit crooked, right? So you're seeing that when you have a static fluid like this, at a particular point, the pressure there is equal, irrespective of how it is. So you see, at this point, A, B, C, D, no matter how the shape of the base change, since the fluid is static, are you okay? The fluid is in equilibrium, and then all these points are at the same position, right? With respect to the base, this side. So this is the height. So this is height, right? So far as the points are the same line within the system, we see the pressure at that point are equal. Okay, so that is the same thing here with this particular thing. So if if I happen to punch a hole here at the opposite side, it should have the same speed and velocity. Or because I'm using freehand, that's why it's not showing that well, right? It should have the same velocity or coming out the same way, right? That's what it says here. Okay, yeah. So irrespective of the position within the system, the pressure at that point is equal in all directions. So what have we written here? Pressure is the same at all points in the horizontal plane in the given fluid, regardless of geometry. Okay, so this is the geometry I was talking about. Sorry, the geometry is how the base is, right? Because they are in the same plane, horizontal plane, right, and the fluid is static or in equilibrium, the pressure at that point are all the same. Okay, provided that the points are interconnected by the same fluid. This is also a very important point. So he's saying that for the pressure at the A, B, C, D, E, F, G, H to be the same, first the system or this fluid here must be in equilibrium, right? It must be static, and then irrespective of the geometry of the base, yes, it should be the same. And then the fluid in all directions, all that point should be the same. Are you okay?